Okay, the next section of the book here goes through and talks about solving radical equations by graphing. I'm going to read through their explanation, which I expect will sound confusing when I read it out loud, but I'll be able to show you some images that'll make sense of what we're saying. So we'll all be confused together for a moment, and then we'll make sense of things. To solve a radical equation, so a radical equation like this, using the graph of a related function, solve the equation for 0, and then replace 0 with f of x. Okay, so solve this for 0, so make it equal 0 instead. Subtract 4 on both sides, get to this, and then replace that 0 on the right side with f of x. The values of x for which the function equals 0 are the zeros of the function and occur at the x-intercepts of its graph. The solution or roots of an equation are the zeros or x-intercepts of its related function. You can also, a second way to do this is you can also solve a radical equation by writing and solving a system of equations based on the equation. Set the expressions on each side of the equation equal to y to create the system of equations. So square root of 2x plus 5 plus 1 equals 4 becomes y equals the square root of 2x plus 5 plus 1, and y equals 4. And these y's are the same y's. These two things are equal to each other as defined in the equation up here. The x-coordinate of the intersection of the system of equations is the value of x where the two equations are equal. Thus, the x-coordinate of the point of intersection is the solution to the radical equation. All right, I think that was pretty messy sounding when I just say it out loud and try to make sense of all those words together. So let's look at it on a graph. So that's what we're doing. We're doing graphing. I'm going to look at the second one first. So what we're going to do first, we're going to do square root of 2x plus 5 plus 1. That is what we've just described there. Any x value that we put in, the domain is limited because at some point we start doing negative radicands, which we don't want. So the domain's limited to, looks like negative 2.5. And as we put in these different inputs, we get out different outputs. Okay. Now we want to say that equals 4. So I'm just going to type in a 4. I guess I'm going to type in y equals 4, like they said to do. That's so when does this equal 4? That's what we're asking, right? We're saying, when does this equal 4? For what x value does this whole thing actually equal 4? Well, this whole thing equals a bunch of different things, but it equals 4 when x is 2. Okay, so that's why they're using a system of equations to do that. Now, the other one, the one that was talking about zeros and solving for zeros, this is basically all they were doing on the other one. So they, instead of doing what we just did, they'll do this. They'll say 2x 5, and then they'll go minus 3, and that will equal 0. Okay. Basically, we've just shifted this whole image down by 4 units. Okay, because rather than plus 1, rather than having this thing equal 4, they subtract 4 from both sides. Well, if we're doing the same thing to both sides, the equation's still true, right? So this should equal 0, just as much as that equaled 4. And the location where those systems of equations intersect should be the same value still. Should still be that when you put in a 2 to either one of these equations, they get you the intersection of the value 4, this light blue line, or the value 0, this dark blue line down here. So that's what they're getting at. They're basically saying, take your radical equation and either put it into a calculator as is, say this is going to be one line, the left side of the equation's one line, the right side of the equation's one line, and find their intersection. So that would be what occurred here. Or another way, do a little bit of algebra, take away 4 from both sides so it's set equal to 0. You'll have a new line here, and it's set equal to 0. So its intersection will take place at a new spot, but the x value of that intersection will not change. Okay. Moving on after that one, then to example number 5.